to have Jan Vondrak here today as our distinguished lecturer. Jan is a mathematician and a computer scientist working in combinatorial optimization and discrete probability. Jan is genuinely a mathematician and a computer scientist. He has a PhD in mathematics from MIT in 2005 and a PhD in computer science from Charles University in the Czech Republic in 2007. Jan was a postdoc at Microsoft Research in Redmond, Washington for 1 year, and a postdoc at Princeton University for 3 years. And he is now a researcher at the IBM Research Center in Almaden, and he has been there since 2009. So Jan has worked in the past few years on the subject of submodular functions, and he has developed a stunning sequence of results over this time. Submodular functions, as we'll hear about in this talk, were studied since the 1960s in operations research and economics. And in the past decade, they've seen a real resurgence in many areas, in theoretical computer science, machine learning, information theory, game theory. And so Jan has really been at the forefront of this line of work, developing many deep and beautiful results. I'm very happy that in the Distinguished Lecture Series, we're able to have a speaker who is not only a superb theorist, but someone whose research touches on so many other areas of computer science. So please join me in welcoming Jan Vondrak.
Thank you very much. Thank you, Nick, for your kind introduction. It's an honor to speak here on a topic that some of you in the audience have done great work on. And many of you know quite a bit about, as I learned today, but I will assume that you haven't heard much about submodular functions. And I will, rather than giving you a lot of technical results about them, I would like to convince you that they are interesting, and it's a concept that's worth knowing about, because it might be useful in places where you wouldn't necessarily expect it. So let me start with the following thought. And as Nick mentioned, I'm originally a mathematician. In fact, originally I'm a physicist. That was even before I was a mathematician. But anyway, in mathematics, not only in mathematics, there are these two paradigms of approaching research. The problem-solving approach and the theory-building approach. And in many cases, these two overlap, but in their pure forms, these two characters are as follows. The problem solver is motivated by trying to crack a certain hard problem. He really likes the problem, and he will do anything to solve this particular problem. Right? On the other side, the theory builder, she's not so much interested in solving any particular problem, but she's interested in finding out about some structure that actually allows you to solve the problem. Now, if you find some nice structure, maybe that will allow you to solve more problems and more problems. So maybe that's a better approach, but I actually don't want to say that. Both of these have their pros and cons, and if you just try to do theory building, you might get lost in some abstract machinery. So I think both of these have, they both have an important role, but partly this talk is about the role of theory building in computer science, in theoretical computer science. If I simplify even further, one could say that the problem solvers, one day they went off and they started their own field, which is now called combinatorics. The theory builders, they started a different field, which is called algebra. But in practice, both of these paradigms coexist, and they are both important. And I want to mention a quote here by Dominic Welch, a great combinatorialist, who said, "Mathematical generalization often lays bare the important bits of information about the problem at hand." What did he mean by that? Well, he said it in the context of a problem which was actually solved, something called the matroid union theorem. Don't worry about what it means. But what he meant was that often when you abstract out some important properties about the problem, you actually make it more general, but at the same time you make it easier to solve because you are able to see it in a simpler light. When you focus on the pieces of the problem which are really important, you have fewer degrees of freedom, and it often allows you to solve a problem even though you made the problem seemingly more general and more difficult. And I will show specific examples of that in this talk. So that's a theme that I would like to emphasize here, that sometimes taking a step back and making things more abstract can really help you to see the essential pieces of the problem. Okay, so let's get started about submodular functions. Where do they come from, and what is this all about? So we are talking about a field that's called discrete optimization, and this is a field that goes back to the Second World War. Really, it really started in the 40s with practically motivated problems like scheduling, shipments, transportation, logistics, and later this area really took off with the evolution of computers. Now, for two reasons: because computers allow us to run sophisticated algorithms, they allow us to solve problems that we couldn't solve before, but also because computers create a lot of problems of their own in systems, databases, compilers. In all kinds of places you want to optimize things. Like ideally, you want to do things optimally, even though it's not always the case. But you want to solve many problems of the following sort. Now, why do I call it discrete? Discrete means that the problems we are talking about involve some solutions which come from a finite collection of possible solutions. You have a finite number of possible choices. Like you have a graph, and you would like to find the cheapest possible way to connect all the nodes together. Okay, that's called a minimum spanning tree problem. Or you want to cut the graph into two pieces, and you don't want to cut too many edges, connecting links between nodes. So all these problems share the property that the choices that we make are not continuous. You cannot take a little bit of this vertex or a little bit of that edge. It's a 0-1 decision. You either take it or you don't. And what that leads to is some problem where you have some collection of possible feasible solutions, and you have some objective function that you would like to optimize. And that's what we call discrete optimization. Now, the interesting phenomenon is that these problems are often more difficult than problems where the space of solutions is continuous, which I actually found counterintuitive the first time I heard about it, because it seems like if you only have to choose from a finite number of choices, it should be easier. In fact, in the early days of discrete optimization, when some serious mathematicians were asked about these problems, like let's say the traveling salesman problem, where you want to go around, visit n cities in some order in the least amount of time possible. The mathematician would look at the problem and they would say, well, there's no problem here. It's just n factorial possible choices. So just look at them and pick the best one, right? That's a trivial problem. There's no mathematics here. So that's one way to look at it. What we actually want to do, as you probably know, is that we want to solve these problems quickly, or at least in polynomial time. That's what we mean by quickly in theoretical computer science. But let me reiterate this point that these discrete problems are typically more difficult than the natural continuous counterpart of these problems. If you allow to vary these variables continuously, let's say you allow fractions in some sense, these problems typically become much easier. And let me also mention that these problems were at the beginning of theoretical computer science. Really, the notion of NP completeness and NP hardness was developed in the 70s. And I think it's fair to say that if you pick generic, typical discrete optimization problem, it's going to be NP complete. And what this means is that we believe that it cannot be solved in polynomial time. Exactly. So for many of these problems, what we are really looking for are either practical solutions or solutions which have some theoretical guarantees, preferably both. But we have to do something other than trying to solve the problem exactly. Now, let's look at the continuous side of optimization. And when you look at a high level, there seems to be a little bit of cultural difference between discrete and continuous. In discrete optimization, it's a little bit of a zoo. You have all these problems with colorful names: vertex cover, set cover, coloring, traveling salesman. In continuous optimization, it seems to me that these people are somehow better organized. They talk about conditions of optimality, duality theory. It actually goes back to the idea that I showed on the first slide. It seems like continuous optimization is a little bit closer to the theory building point of view than discrete optimization. And when you open a textbook on continuous optimization, one of the first things you will see are the concepts of convexity and concavity. And these are very important because these are simple conditions that allow you to conclude, up to some technicalities that I'm not going into, but they allow you to say that, this problem is easy. This problem is easy because such and such. If you have a function which is convex, and let's say you want to minimize it, then it will be possible. And the easiest way to see that, just intuitively, is that if I have a function which is convex, like this, and I try to search for the lowest possible point, I can sort of walk down. I can just find a direction that takes me to a point of lower value, and I can just keep doing that. And when I find a point where I can't do that anymore, then I'm actually sure that I found the best possible solution. Right? That's a mathematical fact, and it shows that a certain very simple algorithm works very well for these problems. However, things are not so simple for discrete optimization problems. And this is for a variety of reasons. The most obvious one is that in discrete problems, there's no continuous way of moving from one solution to the next. You have to sort of jump between solutions, and things can change in unpredictable ways when you jump to the next solution. But still, it would be very nice if we had some concept like this. If we had some concept like convexity that would apply to discrete optimization problems. And this talk is about one such possible concept. I don't want to claim that it's the only one, but it has seen some success in this direction. And that's the concept of submodularity. So when you look at the concept of being concave, what does it actually mean? Well, there are different definitions, but let's just look at the simple way of describing what it means to be concave. I look at some function, and at some point there's a slope, right? There's some rate of increase of that function. And as I move along the curve, I go up, the rate of increase actually decreases, right? That's what it means to be concave. So let's try to describe a property like that for discrete functions. What could it possibly be? There's no way of moving continuously, but still, we can we can talk about a property which is analogous to this. Is there a question? Or okay. Yeah, if you want to ask about anything, you can ask. So let's talk about functions which assign values to points, to vertices of the cube. We have a cube 0, 1 to the n. So why am I talking about functions of this sort? This is actually a very general framework which allows us to encode all these problems that I talked about earlier. Let's say we are talking about a graph problem and the goal is to pick certain vertices. Right? So I can formally encode that as selecting a 0, 1 vector where n is the total number of vertices and the coordinates where I pick a 1, those are the vertices that I actually picked. Okay? So it's just a formalization. It's equivalent to having all possible subsets of n elements. I have n elements, and to each subset of these n elements, I would like to assign a number. Or equivalently, to each sequence of zeros and ones, I want to assign a number. So discrete optimization, in some sense, is about such functions. So let's see, what could it mean for such a function to be concave? Geometrically, it's not so, it's not so obvious anymore. What does it mean to be concave? But we could talk about a property which is very similar to the definition of concavity that I mentioned before. We can look at the discrete derivatives, which are simply the differences between two neighboring points. I take a point and at the next point in a certain direction, and I look at the difference of these two values. Okay? I call that a discrete derivative. So the property similar to concavity is that when I look at these differences, when I move up in the hypercube, the difference can only become less. Okay? These discrete derivatives are non-increasing. They can only decrease when I go up. This is exactly what concavity means for a real valued function, and we can also define it like this on the hypercube. So that's one way to move from the continuous notion to the discrete one. Now, there are different equivalent ways to say that. Maybe the next one is more intuitive when we talk about functions on subsets. As I mentioned, these can be all viewed as functions that assign values to subsets. And these have natural interpretations. For example, I have n objects, and I have a value for each subset of these n objects. Okay? So what does it mean for this function to be submodular? It means when I look at the so-called marginal values, that's the value of an item added to a certain set minus the value of that set itself. It's the added value that this element brings to that set. When I look at these marginal values, they can only decrease if I add the element to a larger set. Okay? This has a natural economic interpretation. The larger the set of items that I already have, the less I'm willing to pay for the next one. Okay? That's exactly the same property that I described on the previous slide. These are two equivalent ways to describe it. Finally, the way that you usually find in textbooks to define submodular functions is this one, which is very short, but I think it's not very illuminating. It says that for any two sets, if I take the value of the union plus the value of the intersection, that's at most the sum of the values of the two sets. So true, this is the shortest way to define submodular functions, but I think it doesn't really tell you what they are. Personally, I prefer the top one on this slide. When you repeat, if I add something to a larger set, it brings less value, or at most as much value. So, okay, now we are talking about certain properties of functions, but we haven't really seen any actual function that would be interesting and fall in this framework. So there are quite a few such functions. Let me just show you two examples. And these are examples that arise in actual problems quite often. So I would say these are actually two canonical examples of these submodular functions. The first one often arises in situations where you have some kind of universe, and the problem is about covering different parts of the universe. You have some set system, and the function tells you for different choices of these sets how much area they cover. Okay, the function value for set S is the area covered by the sets indexed by S. That's what the function describes, and it's pretty easy to see that this function is always submodular. The other example that I want to mention is a cut function in a graph. So here we have a graph, these are nodes, we have some edges between them, and the function tells you, it's a function now on subsets of vertices, and the function tells you if I pick a certain set of vertices, how many edges are leaving this set of vertices, how many edges are between this set T and the other side of the graph. This is called a cut function because this is how many edges you have to remove to separate the graph into these two pieces. Let's say T and T complement. So this kind of function is also submodular. Okay, so this is the way that submodularity is tied to many classical problems in, let's say, theoretical computer science, but you might still ask why is it practical at all? I will come to some more practical applications of this later, but it will be also a little bit more complicated to explain. So these are the two simplest examples that I can give. All right, so let's come back to this question of convexity. We defined a certain concept here which should be helpful for something. So far, I haven't told you why it's actually helpful. But if it's supposed to be helpful in the same way that these functions were helpful in the continuous domain, it should somehow correspond to being either convex or concave. And through that property, it should allow you to solve some problems. So is it actually like convex or like concave? This question is not discussed very often because convex and concave looks like the same thing. You just flip it around. But actually, it makes a difference for optimization problems. Namely, when you flip things around, maximizing becomes minimizing, and that's not always the same thing. So let's see. Is it like concave or is it like convex? Well, my initial explanation of what these functions are and how I define them was actually motivated by concavity. It was like going up and then going down, right? That's concave, that's not convex. So that would be an argument for why these functions somehow capture the discrete notion of concavity. But there is an argument for why these functions could be viewed as convex. And that argument actually looks stronger. So what is this argument? The argument is that submodular functions can be, in fact, minimized efficiently. And this is a milestone result in discrete optimization, one that was awarded the Fulkerson Prize. And it's a very general result. It says if I give you any submodular function, and the only way you can access the function is to ask what is the value of this point, what is the value of this point. Just having this very weak access, you can find efficiently in polynomial time the exact minimizer of that function, the point where the function is minimal. And I listed several different papers here, so let me say what that means. The first result was a solution by Greshel, Lovaas, Schreiber, not a practical solution, one that works in principle using ellipsoid method, a pretty slow algorithm, but later in 2000, algorithms were found which are combinatorial, actually still quite complicated. but combinatorial algorithms, which work in practice. So these algorithms are quite complicated. I'm not going to describe these algorithms here. I want to say a little bit about why in principle it is possible to minimize these submodular functions. Why is it that we can minimize them even though they look kind of concave? That looks like a contradiction to me, but there's a geometric kind of explanation which tells you why this is the case. There's actually a pretty simple way to take this submodular function and replace it by a continuous function, which is convex. It's an efficient transformation in the sense that I can, evaluate this new function if I was able to evaluate the old function. Let me not talk about it how exactly you do this transformation, but it's not very complicated. You basically extend a function which was defined on the vertices of this cube. You replace it by a function which is defined everywhere, also inside the cube, and it's continuous, and it happens to be convex. And once we have that, it's plausible that you can actually optimize the original function. You can minimize it. Because for a convex function, we know that you can, let's say, keep walking down, and you can reach the minimum in principle up to some convergence issues. But you can minimize this continuous convex function, and you can actually also see that this point will correspond to a vertex of the cube which minimizes the original function. So this geometric connection tells you that submodular functions, in some sense, really correspond to convex functions rather than concave. And that's the reason why you can minimize them. So this is a beautiful theory surrounding this result. The combinatorial algorithms that solve the problem more efficiently are actually complicated, as I mentioned, and I'm not going to talk about them. But this is a strong argument for why these functions are kind of convex. Now, what happened in recent years was that a number of applications came up where you actually need to maximize these functions. And I will show a bunch of them. So at that point, one can ask, are these functions just convex, or is there also some concave aspect that you can exploit to maximize them? And the concept that I defined looks like concavity. On the other hand, we know that many of these problems that can be phrased as maximizing submodular functions are actually hard, are provably hard. So there's something surprising going on here. It looks like these functions are not as much concave as they are convex. But the situation is not as bad as it looks. And the explanation or partial explanation of why these functions actually can be also maximized quite well goes back to work in the 70s, Nemhauser, Woolsey, and Fisher, who actually proposed a very simple algorithm. A very simple algorithm for maximization of these functions. And although this algorithm doesn't solve these problems optimally, it actually solves them pretty well. So what is this algorithm? This algorithm is called a greedy algorithm. And the name pretty much describes what the algorithm does. The algorithm includes elements one by one. And every time you pick the next element, trying to maximize your gain. And you never backtrack. You just pick the next element, trying to gain as much as possible in terms of the objective function. And they proved a number of results. But maybe the most basic one, and also actually the most useful one, is that this algorithm works pretty well if you just want to find, let's say, k elements, some fixed number of elements, whose value will be as large as possible. This algorithm will do it pretty well. It will not find the very optimal solution, but it will find a solution whose value is guaranteed to be at least some fraction of the optimal solution. And that fraction is this magical number, 1 minus 1 over e, which is roughly 63%. But this is in the worst case. Actually, in practice, this algorithm often finds solutions which are much better than this, pretty close to optimal. So I think from a practical standpoint, this is really the best kind of algorithm you would like to have. It's very simple to implement. Runs pretty fast, and it finds a solution which is usually very good, and it's never worse than this fraction, 63% of the best possible solution. So let me show you three places where this has found application recently. And these are three applications that maybe explain why there has been more interest in submodular functions, because each of these applications comes from a different direction. And these are problems where you wouldn't necessarily think about submodular functions in the first place. So let me start with the first one. The first application is problem of spreading of influence in a social network. So this was a paper by Kempy, Kleinberg, and Hardoch, which has been quite influential, and it's about influence. The story they had was the story of viral marketing. So the problem here is that you have a social network. Let's say the picture here is a graph where the nodes are people. There are some links between them which mean that, say, these two people are connected, they're friends, but these edges also have some number associated with them which tells you how strong the link is. In fact, the number means that it's like the probability that what you believe will be transferred to your neighbor in the network. Okay? So the process that this paper studied was that you would like to initiate, you would like to activate certain nodes in the network in the sense that maybe you advertise some product, or you tell them about some new product that you would like to be widely known, but you only have a limited amount of resources that you can spend on it. So you would like to tell certain people in the network about this product. Okay? And once you tell them, the process will propagate, and these people will tell their friends about the product. But this only happens with some probability. Let's say if you're friends with the next person and you have a 0.5 on that edge, it means that with probability 0.5 you will tell the next person about the product. Okay? So the information spreads in the network like this. Every node which is activated will activate its neighbor with a probability which is on that edge. And you just keep repeating this process. It's some random process which keeps running until there are no more neighbors to be explored, and you end up with a certain number of nodes activated in the network. So it looks like a complicated process, but the authors of this paper noticed property which is not even that difficult to prove once you see it, that the function which tells you the number of nodes, the expected number of nodes activated at the end of the process, is a submodular function of the set of nodes that you activated in the first place. Okay, so depending on the nodes that you activated in the beginning, you will end up with a certain random number of nodes at the end, but the average or expected number of nodes that you activate at the end is a submodular function of the nodes that you started from. And this is very useful because it tells you that the greedy algorithm will work reasonably well. You don't have to try out all options of what nodes to expect, but you can sort of choose them one by one. Now, there's some additional work that goes into that, but this high-level point of view allows you to come up with some approach that maybe you wouldn't come up with otherwise. The second application that I want to mention is a sequence of work which has been spearheaded by Krause and Gestrin, and it's on gathering of information in various domains. And they have a sequence of papers dealing with all kinds of problems where you want to gather information in some environment, and you are limited in terms of how many sensors you can place in that environment. Now, each of these settings has some specifics of its own, but there's something that these settings all share. The setting is always that you have some limited number of sensors, and you would like to decide where to place them, and you have some notion of what benefit those sensors give you, depending on where they are placed. And you can imagine that it's not just a simple sum of what each of these sensors tells you, because if you place two sensors very close to each other, they will give you essentially the same signal, so that's not very beneficial, right? The benefit that you get from placing all these sensors is really a function of the combination of all these sensors that you have chosen. So the objective function that we want to maximize here is some notion of information that we gather from these sensors. And now it happens that this function often is submodular. The applications vary a little bit. There's no single argument which explains why this always works. But it's often related to the following fact from information theory, which is quite useful. If you look at the entropy of a collection of random variables, this entropy is a submodular function of the particular subset of variables that you have chosen. And this works even if these random variables have some complicated dependencies between them. In fact, that's the whole point. So let me repeat this. The variables which would correspond to where you place these sensors give you some benefit in terms of the information that you learn from them, which happens to be a submodular function of the set of particular sensors that you have chosen. So this has been useful in a number of different settings. Let me mention one, which was an actual competition. So this was a competition held at the Water Distribution Systems Analysis Symposium, 2006. And what this symposium is about is like optimizing water networks. And they had the following kind of competition. They have an actual model, description of some huge water network with all kinds of components. They have like pumps and tanks and valves, and they describe to you how it all works, which direction the water is flowing, how fast, and so on. And then there's some possibility of random outbreaks of contamination in the network. Okay? You don't know where exactly these will happen, but you know, let's say, the distribution, how these outbreaks are distributed. And your goal is to place certain sensors in the network so that you can prevent as much damage as possible from these outbreaks. Let's say the outbreak happens somewhere, it will propagate throughout the network until it hits some sensor, and then some actions can be taken. But before it hits any sensor, it will cause some amount of damage. So what is this competition about? Well, you have to come up with an algorithm which, given the description of the whole system, which is pretty complicated, will decide where to place these sensors. And what this group of authors did was that they proposed a very simple algorithm at the high level, though the algorithm had many more details, but the high level idea was the following. Well, what is the actual benefit from placing these sensors? You can formulate it as some big objective function, which was quite complicated, but they were able to show that this function is actually submodular. And intuitively, it makes sense for a reason similar to what I described on the previous slide, that somehow having a certain configuration of sensors determines what the benefit of the next sensor will be, depending on its location. But if I have more and more sensors, if I only add sensors to my collection, this cannot increase the benefit of some other sensor out there. Right? That's something that's intuitively plausible, and they were able to show that this is actually true. And based on this, they designed an algorithm which was essentially the greedy algorithm, except the actual objective function here is pretty complicated. It involves a lot of simulation, and there was a lot of other work that went into it. So it's not just a greedy algorithm, but this high-level approach was actually able to defeat many other approaches which were like looking at the topology of the network more closely and trying to do something smarter by running some algorithm on that graph. This pretty simple high-level approach actually defeated all the other algorithms, and they won the first prize. So that's interesting. And let me go to the last application that I want to mention. This is in the area of, this was actually at the beginning of one important direction in algorithmic game theory in 2001. And this was the problem of combinatorial auctions. So what is a combinatorial auction? In an auction, we want to sell something to some agents who are interested and are willing to pay certain amounts of money. In a combinatorial auction, we want to sell multiple items. The reason it's called combinatorial is that there's some combinatorial explosion here in terms of describing what the preferences of these agents might be. You have M items, and now any combination of these items might be preferred in different ways by these different agents. So it can become a difficult computational problem pretty quickly. Plus, there's another issue here with the incentives of the agents to report what they actually believe about the value that they are willing to pay. But let me put that aside. I'm not going to talk about the game theoretic aspect in this talk. Let me just describe the problem of allocating these items optimally. And this can arise in many settings. You have some items, and you want to allocate them to some agents under the objective function that you want to maximize the total amount of utility that these agents receive from the items that they got. Right? So there's some notion of value that the agents have. And depending on the particular items that they receive, they have some degree of happiness, which is captured by these valuation functions. Now, this is an optimization problem. How do I allocate the items so that everybody together is as happy as possible? And in general, this problem is very hard. If I just ask you like this, given arbitrary valuation functions, even if I assume that they're monotone in the sense that adding items can only increase the value of the function, it's still very hard. But there's one setting which has been studied quite a lot, and that's exactly the setting where the valuations satisfy the property of diminishing returns, in the sense that the more items I have, the less I'm willing to pay for some fixed additional item. And in this setting, it's more tractable. You can develop some interesting algorithms for this problem. In fact, the greedy algorithm, just off the shelf, already gives you a pretty good result for this problem. And this was also part of the work of Nemhauser, Woolsey, and Fisher, even though it doesn't fall in that simple framework where you just want to pick k elements. This is a little bit more complicated. But the greedy algorithm, which also has a natural interpretation here, gives you 1/2 the approximation. So it gives you a solution whose value is at least 1/2 of the best possible solution. That's not so bad. At the same time, there's a host of other problems where similar results were proved earlier. And sometimes, these are separate works that somehow didn't know about each other. But when you look at them through the prism of this submodular maximization, they all become the same problem. These were problems like the coverage that I described, like you want to select k sets that cover as much area as possible. This was studied earlier. Several variants of allocation problems where you want to allocate items to bins or to agents, and you want to optimize different quantities. For several of them, it just happened that this kind of result was proved, and it's not a coincidence. All these problems can be formulated as a problem where you maximize a submodular function subject to some simple constraint, and that's the reason why you get all these coinciding results. So it also has some unifying power. This kind of framework tells you the reason why certain results are possible. All right, so that brings me to the last part of my talk, which is some of the most recent work, which I've been personally involved in, which is essentially what can you do beyond the greedy algorithm? When you look at the message that we have seen so far, it's that these are problems where the greedy algorithm performs pretty well. It's a pretty practical solution. But it turns out that the greedy algorithm has its own limitations. There are versions of these problems and extensions where the greedy algorithm simply breaks down, where it doesn't work at all, such as if let's say you just replace the condition that I want to pick k elements. I replace that by saying that I want to pick elements whose total size does not exceed a certain capacity. Like each element has its own size, and they add up to some amount that doesn't exceed 1. That's a very simple modification of this constraint, but you can't just run the same greedy algorithm anymore. You have to do something a little bit more sophisticated. Also, the question of maximizing non-monotone submodular functions was not understood very well. Like this cut function that I described, it's not monotone, but it's still, there's no reason to believe that you cannot do the same things that you can do for monotone functions, for these functions as well. So what can you do to go beyond this one particular algorithm? Can we develop some more general, more robust framework which would allow us to solve problems of this kind? And that's, I will try to say a little bit about in the remaining time that I have. Maybe 5 minutes. Okay, so let me step back and let me mention the following. In the history of discrete optimization, there has been one connection which was very fruitful, and that's in terms of both the theory and practical applications. And that's the connection between discrete optimization and linear programming. Now, linear programming is a field that we understand pretty well now. We have very practical solvers for linear programming problems, and this ability has been also useful to develop algorithms for discrete problems. Now, for the problems that I talked about here, which involve some objective function which is not linear, it's more complicated, namely it's submodular. As we saw early in the talk, we have some notion of a continuous relaxation when we want to minimize such functions. That's the notion of Lovász extension, which makes the function convex, and then you can minimize. And that's very nice, but this doesn't seem to work for maximization problems. Okay, so the meta question that we asked here was, can you have some some framework for maximizing these functions, for solving problems like the ones that I described here, through some more general optimization network framework, something like the framework of linear programming. And this is the framework that seems to work quite well, and it has been successful for a bunch of these problems at least. Now it has seen quite a lot of development in the last few years. And it's something that we call multilinear relaxation. So in fact, it is a natural extension of the notion of linear relaxation, linear programming. And what this relaxation does is that it takes your discrete problem and it replaces it by a continuous optimization problem, where the function that you are going to optimize, the new continuous function, is obtained as a multilinear extension. Now, this is a technical term which might sound very advanced, but it's actually a very simple kind of extending the function. What you do is for point x, which has some fractional coordinates, you replace it by a random 0, 1 vector, where each point is replaced randomly by 0, 1 with probabilities corresponding to these coordinates xi, and you take the expectation of the resulting function value of this rounded point. That gives you some continuous function, which happens to be a multilinear polynomial. That's why we call it multilinear. But this simple transformation seems to do for maximization problems what the Lobas extension does for minimization problems. Namely, it allows you to have a continuous version of your problem which can be solved more easily than the discrete problem was. And then given the solution of the continuous problem, you can go back to your discrete problem and get some useful solution there. Now, the way you actually do that depends on the particular problem, but at the level of solving the continuous problem, the continuous version of your problem, it's actually pretty simple. And you can solve it using the same approach for all kinds of problems. And this is a continuous version of the greedy algorithm. So actually what is happening here is not mysterious at all in hindsight. It's similar to what is happening with linear programming. If you replace this discrete problem by a continuous one, typically it becomes easier. And the same thing happens here. You replace your problem by a continuous one, and then you can run a continuous version of, let's say, the greedy algorithm, and you can find a solution which is, in this case, not exactly optimal, but it's pretty close to optimal. Namely, it has the same guarantee that we saw earlier. It's at least 1 minus 1 over e times the value of the optimal solution. So this framework, the first application of this was the submodular welfare problem, the combinatorial auctions that I described. For this problem, it actually gives the optimal 1 minus 1 over e approximation. But since then, it has seen a bunch of developments in different directions. Let me say at a high level, let me not go through them in detail, let me say at a high level how this framework is useful. So for one thing, it allows you to solve these problems in a more robust fashion in the sense that you can throw in more additional constraints to your problem, and it doesn't change the difficulty of the problem too much. The discrete greedy algorithm, if you add some additional constraint, it suddenly breaks down. This behaves in a nicer fashion in the sense that it still works, you just lose a little bit on the performance of the algorithm, but you can still use it. The second thing is that it actually allows you to prove that some of these algorithms are optimal. Now, this is a more theoretical contribution, but it allows you to match the results, the positive results of what we can do, allows you to match them with results of what we cannot do. And often you can conclude that these are actually the best approximations that you can achieve for these problems. Lastly, this has interesting implications in the area of truthful mechanism design, but I really didn't have time to talk about it, so I'll just leave it aside. So let me wrap up. I think it's about time. So the high-level message here is that these problems with submodular objective functions have much more modeling power than problems where the objective function is just linear. And this is similar to going from linear continuous functions to, let's say, convex functions or concave functions. So there's some modeling power here which is good to keep in mind because it turned out to be useful in several different places. And moreover, we have a framework for these functions now that allows us to solve problems of different kinds in a relatively versatile manner. That's the framework of multilinear relaxation that I mentioned. Now, where is this going next? Well, maybe the most ambitious goal, which I don't know if it's plausible, but it could be true in the sense that you can solve any convex optimization problem almost as well as you can solve a linear one. It could just be true that you can solve any problem with, let's say, monotone submodular objectives as well as you can solve the linear one. There's no jump in difficulty. You can basically do anything that you can do with linear objectives. You can also do it with submodular objectives. We don't actually know that this is impossible. But maybe on a practical level, more important considerations are where can these algorithms be actually used? Now, I didn't say much about the running time of these algorithms. They are not that fast. They are not as simple as the greedy algorithm. But they are not completely impractical. We have actually some recent work with interns at IBM which make these algorithms quite practical. So I think they are worth considering, at least, if you are faced with one of these problems. And the last point is that there have been several applications where this concept of submodularity has been very successful. But I think there might be more if this concept was more widely known. So I think it's something that's, it's not a solution that would solve all the problems in the world, but it's something to keep in mind if you are looking around for possible solutions. Could this hammer be useful for my problem? Just knowing about it, that it's out there and it's possible to use it, I think might be useful in many settings. So I think I'll finish on that note. Thank you.
So we have plenty of time for questions. Does anyone have a question for Jan?
Yes.
I was really happy to see this work on multilinear optimization. I think it's fascinating. I also found the introduction of your talk very thought-provoking because you started talking about continuity, but somehow you found continuity and took something smaller, which was just convexity, and you made a mapping into that. But continuity is something that is very useful even in global optimization when you don't have, like Lipschitz optimization and so on. Bounds are very useful. So indeed, there seems to be something more general than just convexity that is very useful to do optimization. Have people made a connection with, say, things like what people do in nonlinear optimization, sorry, in global optimization, like using Lipschitz bounds?
That's a very good question. So certainly I didn't intend to make the impression that convexity is the only possible thing to look at. I think that maybe the reason is that on the discrete side, we are a little bit behind, and we haven't explored as much as people have explored on the continuous side. For Lipschitzness in particular, I don't think somehow that it would be useful on its own in the discrete world, just knowing that values don't change too much when you go to the neighbor, something like that, right? Could be reasonable, but I think somehow in the discrete world, things are more difficult and more hairy than in the continuous world. So Yeah, I don't have a definite answer to this, but certainly the story is less developed on the discrete side than it is on the continuous side.
I was a little bit surprised to hear you say that, for many of these problems, it appears to be the case that the 1 minus 1 over E is not only what the greedy algorithm does, but it's the best you can do. Because, there are a lot of combinatorial optimization problems for which there are better approximation algorithms, right? So I'm kind of wondering whether I just got the wrong impression that, when we talk about submodular function optimization, really it's the majority of the problems for which you can't hope to do significantly better.
Sure. So let me make 2 points here. One is that certainly there are many problems out there for which 1 minus 1 over E doesn't play any role. It's for some subset of these problems that I mentioned where it actually turns out to be the best approximation you can achieve. The second point is that this is the best approximation that you can achieve in the worst case, theoretically. So even for these problems, it's not a reason to believe that you cannot solve many practical instances much better than this factor. But from a theoretical point of view, this is the best you can achieve for a certain group of these problems that I talked about.
But how big is this group really? I mean, do you think out of all the problems that you're aware of, is it like,
No, I'm
half
not.
of them, 10%?
No way, no. This is these are pretty special problems. So these are problems that have this interesting property of submodularity.
But I mean conditional on this, right? Take all the submodular problems that you know of. All the discrete problems on which you can have reasonably attack them with submodular functions. Which fraction of those do you think you can prove that it doesn't get better than 1 minus 1 over E in the worst case?
Yeah, I don't want to put out numbers like what fraction, but these problems can be divided into several categories. And for one category of these problems where you maximize, it's a monotone submodular function, it's a pretty simple constraint, somehow this is the right answer. There are many other problems, let's say for minimizing submodular functions, where the story is completely different and this does not happen. So it's a pretty special group of problems. I certainly don't want to claim that this is a huge class.
Since Holger didn't ask something empirical, I will. You at the end sort of raised the question about the practical impact of submodularity rather than the theoretical impact, which I guess is hiding to me on the slide now. And I wonder, what do you know about? So of course, in practice, when we face combinatorial optimization problems, we very often solve problems for which theoretical guarantees are terrible. Practically, combinatorial functions that really happen really involve solving huge subpacking problems that would be terrible in the worst case, and they just do it anyway. What do you know about the empirical impact of submodularity? I know that sometimes we can't get better worst-case guarantees than 1 minus 1 over E or something like that. But do we know that this tends to help in practice?
Well, it helped in several cases at least that I'm aware of. I mentioned some of them here, but maybe in the area of combinatorial auctions, if you look at the area of combinatorial auctions specifically, I think it's fair to say that the role of submodularity has been more on the theoretical side of things. It hasn't been really used in practice in actual combinatorial auctions. I think that's a fact. So yes, it is primarily a theoretical concept, but it has seen some empirically successful applications. I think it's good to keep in mind some theoretical concepts and to be aware of them, even if your final goal is to develop something that works in practice. It can guide you in how you think about the problem. I think the water sensor networks challenge was one example of that, where it's not just some problem where you say, it's submodular, so I know how to solve it. But this theoretical concept is useful in guiding you how to think about the problem, like how to grasp it at the high level. And then you can go down and figure out the technical details, which might be hairy, but still it might be a useful concept to know about.
But I guess that's a case where they use the greedy algorithm, right?
That is true. That is true. Yeah.
What I'm wondering is, it seems just tempting to conjecture that if I just used a mixed integer programming solver or something to solve a problem that happened to be submodular, that it might be better than if it wasn't. And I wonder if you think that conjecture makes sense, and if so, what do you think a theoretical building blocks for trying to establish that would look like?
So I'm not sure about this, that if you just use a generic MIP solver for some of these problems, that it will do very well. I mean, it will probably do pretty well on some problems which are theoretically impossible to solve. But if you have this solution which is very practical, very fast, plus it has a theoretical guarantee, then you are just very lucky, right? That's a situation that doesn't happen very often, but if it happens, then I think that's great. I don't know exactly what the competing algorithms were in this water network battle, but I think they often used some machinery like integer programming solvers, and in that particular challenge they didn't do as well. So I think these are situations where theoretical point of view can be helpful. I don't want to make claims about how large the fraction of problems is that this solves, but I think it is useful.
So 1 minus 1 over epsilon is the best you can do if you only know that it's submodular. But if you're more, so it's related to this question, if you know more about the problem than it's just submodular, is there something better than you can do with it?
There are some improvements, yes. There are improvements based on some additional knowledge. There's something called curvature of a submodular function. Actually, it's a notion of how close to a linear function you are. You can imagine that there's some spectrum of functions between linear and submodular functions, and the closer you are to linear functions, the better you can do. So there's actually some quantitative notion of that and some results along these lines. So yes, you can do this kind of stuff.
So to continue with my questions, trying to map the continuous in the discrete case. So in the continuous world, folks have also learned the value of regularizers, of adding on to regularizer, L1 regularizers to make the problem have nicer properties, get better convergence rates, and so on. Of particular interest is L1 regularizers, which also provide another mapping between discrete optimization and with the L0 norm in optimization, continuous optimization with the L1 norm. Via compressed sensing, which Nick covers in this course. So, have people explored the use of regularizers with submodularity, or try to make connections to compressed sensing?
I'm not aware of something like that. So this is in the context of machine learning, regularization, or
actually. Uri would be upset with me if I say it's machine learning. It goes back to, I think, geophysics, where people often have a cost function and they have an L1 norm. What they really want to add is an L0 norm, because they just want to know which, say, bases are active or whatever, or which components are active. So the original problem is NP-hard, but if you replace that by one with an L1 norm, so it's very similar to the linear programming setting. And provided that the problem is sparse, if you add the extra assumption, you can actually show that one solution with hyperbolic is a solution to the original problem.
Yeah, I'm not aware of something analogous to this. I don't know if Nick has a better answer.
I'm also not aware of these techniques being used.
Maybe I'll just make a comment on Nando's work. Francis Bach has been working quite a bit on, the use of submodular functions and Lovász extension for the solution of sparse problems in machine learning, especially for fear. So I think that's one very interesting application, definitely, of how you can think about L0 optimization and L1 and sparsity, you know, in the context of what we've been speaking. Just in terms of the practice, sort of what are the typical sets we're thinking of? So if I wanted to actually apply this, what is the size? Because it seems like the greedy is necessarily a sequential kind of algorithm. So if I wanted to parallelize, are they like theorems that let you work on small subsets and do greedy and combine? Yeah, just general thoughts on the practical use of these methods.
There has been some very recent work on parallelization of this. There has been some work on implementing the greedy algorithms in the MapReduce model. I can't really speak to how practical they are. It is true that inherently these are sequential algorithms, so they are not very easily parallelizable. And even the greedy algorithm, as simple as it is, people have actually tried to find further heuristics to speed it up, to make it even faster for these huge data sets. Like the water network, they actually had some additional tricks. They didn't just use the greedy algorithm, they had some speeded up version of that. So, of course, if you want to use these concepts in practice, there's a lot more work to be done.
Going back to Kevin's question about practical applicability. So actually in that water network challenge, I believe one of the reasons that greedy was doing really well was that it could actually use all the data. There were like 10 million data points or something like that, which all the other methods, like they used IP solvers, but then they used maybe a subset of 100,000 points for which the IP solver would scale, but then they didn't use all the data, so they didn't do quite as well. And they also didn't have all the speed up tricks that L had. But relating to that, so you talked about the LP relaxation, and you know that's underlying IP solvers. You do the LP relaxation on each node in the graph and use that to bound your objective function. How about this multilinear relaxation? Could you do something similar there? Use that as a part in an IP solver or something like that for submodular functions to get speed up there?
I see. To use it directly to find an integer solution to your problem. Yeah, frankly, I don't know. I haven't thought about it. Maybe it's something to think about. Yeah. The way we thought about it was the way these techniques are usually used in approximation algorithms is that you actually solve the fractional version of the problem and then you work with it further. Yeah, but it's something to think about. Yeah.
I mean, you wouldn't get a guarantee like an LP. You would only get bound because of the 1 minus 1 minus epsilon, but it could still be, you would still get a bound. I guess.
It might be possible. Yeah.
I'm wondering, greedy algorithms in discrete optimization on the practical side are often just used as the first stage of a scheme for finding good solutions, right? And the classical example is the TSP. If you want to solve that for real, you might start with some sort of greedy tour construction, and that even has an approximation guarantee if you do it right. But you would never stop there. You would then start doing, exchange moves on the candidate solutions. So the same potential seems to exist when maximizing submodular functions, right? Except for the cases that you mentioned earlier, where you can somehow prove that in the worst case you can do better. I'm wondering, do people actually do that? And maybe more to the point, do you see hope in, at least in special cases, for specific problems? I mean, showing that having a carefully constructed second stage can even give you a better approximation guarantee than greedy alone?
That's a good question, and so as a theorist, I admit that we often stop at the point where we prove a certain approximation guarantee, and if we know that that's optimal, even better, we just stop there. But in practice, you want to go further and try to improve the solution, because in many cases it could help you further. That is true. You asked whether you could prove some kind of guarantee for this second stage improvement, well, I guess if you want to try to prove some guarantees, it should be under some additional assumptions, or maybe under some stochastic model of where the instances come from, right? In the worst case, we know that that's the best you can do, but yeah, there's certainly room for more work. So certainly that's something to try.
Maybe I can just make one remark. So often in I'll get back to that. So often when we talk about the hardness of a problem, right, we might say that for maximum K coverage or something, 1 minus 1 over E is optimal, assuming P is not equal to NP. Right? So if you could do better than this, then you would prove P is not equal to NP. So an interesting feature about submodular functions is that these guarantees can be proved optimal without any complexity theoretical assumptions. So for submodular maximization under these simple constraints, 1 minus 1 over E is optimal under no assumptions whatsoever. So worst case without.
So you again place a lot of emphasis on this. Then let me ask you the question that I asked Jan earlier. Maybe you're more courageous. What fraction of discrete problems, maximization problems that are submodular, do you think are optimal, are tight in that sense?
Yeah.
I get the impression that you both seem to believe that it's a fair fraction of them.
In some sense, I mean, it depends what one means by natural. So if one is
Things that might have applications.
problems that one tends to encounter in practice, maybe it's true, right? I mean, if I'm walking around in the forest of computer science research, I often encounter natural problems, like vertex cover, set cover, maximum cover, and so on. Yeah, so these problems that I do encounter often are ones for which we know the optimal answer. So. Okay, now I should get back to Alex.
Are there any other upcoming set function properties which seem promising to show good optimization properties, like submodularity? Like, are there like generalization of submodularity or other kind of set function properties?
Yes, there are other classes of functions which have been studied, and in fact, the whole question of what does it mean for a discrete function to be convex or concave, I think doesn't have a unique answer. And there's a theory of discrete convexity which has been developed primarily in Japan for some reason. There are several classes that have been studied, and they're not very widely known around here. The theory of these functions, they're called like L convex, M convex, L concave, and so on, is it is a little bit more hairy. I think for some reason submodular functions are pretty clean, and also the surrounding theory is kind of clean. There are other competing theories which have some advantages. They can solve some problems that submodular functions cannot solve. So there are other classes of functions to look at. As far as I know, and this is my biased opinion, submodular functions are somehow the cleanest one. But there are other related classes.
Okay, we're running pretty late into the evening, so maybe we should draw into the questions here. So let's thank Jan again for